Welcome Mechanics of Materials students. This example problem demo gives us some insight into what we can do combining concepts of small angle and small scale displacement with Hooke's law stress-strain relationships with elastic constants. So in this case, we have two bars, B to P and A to P. They're made from a material we know, and because we know what the material is, we can look up our elastic constants. And in this case, we're only going to be really concerned with normal stresses and strains. So the only elastic constant that's particularly relevant in this case is our tensile modulus, and it's 200 gigapascals, or 200 times 10 to the 9th newtons per square meter. And in this case, we've got a state of constraint here. Both of these bars kind of end on what looks like a roller or a pulley, and for whatever reason we know or don't know, a force can be applied. Maybe we're hanging a load off of it or something. Maybe there's a weight down here, or it could be leading to another piece of machinery that has that's applying a force. But in any case, we know that as the result of this force application, that this roller is going to displace a certain amount down the bearing slide here. And we know that that displacement amount, something we could measure, maybe there's a sensor on the side of the bearing, we were able to measure that, it's very small. It's 0.25 millimeters. Now, in kind of in a real life situation, where would that matter? There could be some limit that we can't have this point deflecting, traveling further down. We may know what weight we're going to have to apply. We know that we don't want point P moving more than a certain amount. And we may be looking at a choice of materials and cross-sectional areas for AP and BP bars, or we may have, as we do in this case, we have a fixed area. We have bar cross-sectional area of 100 millimeters squared, which we can convert over to meters. So we've got 10 to the 3rd millimeters per meter squared. So we're going to end up dividing by 10 to the 6th. So we have 100 times 10 to the minus 6 meters squared, or 1 times 10 to the minus 4 meters squared. Okay. Have our bar area. And what else? What other information? So that's fixed. We have a fixed material for the bar. That's fixed. Area is fixed. So with a fixed modulus and a fixed cross-sectional area, now we've established, the first part of our relationship to how much force the bars can pull back with, basically. We don't have an ultimate stress that they can handle, but so we will assume at this point that we're well within the elastic limits, so nothing's going to yield, so we can use everything we know about elasticity to answer the question. So AP length is originally 200 millimeters, or 0.2 meters, and P to B is originally 0.25 meters. Okay, so we need to relate what we know about the bars. We have materials, we have modulus, we have cross-sectional area, we have displacement. And so we kind of need to know what the resultant strain is in these bars, from which we can use the modulus to get the stress and the force, and then we can go back and do an FBD with those forces about point P and get the net downward force. So that's basically the approach we're going to take. So given that we have fixed modulus and fixed area, we could assume that AP and BP are maybe an established system, and we maybe have a limit of, okay, 0.25 millimeters is the max deflection we can tolerate. This tells us how much force can you apply. If we had a fixed force, we could work it back the other way and say, how much is it going to deflect? Is it too much? And go back and forth that way. So now that we have an approach, our first step is going to be to find the strain, the axial strain in, we'll call it E axial in AP and E axial in PB. And for that, we're going to use relationships between small deflections and original orientation. We'll change color here to do that. So use a lime green. So we know that for small deflections, we can make the approximation that the hypotenuse of a right triangle is pretty close to one side of it. So for that, we would use this relationship where we have our known deflection of 0.25 millimeters. And from that point that is 0.25 millimeters downward, vertically downward from P, we drop a perpendicular to a point on the extension of AP. So basically AP is going to be this configuration, so we're looking for that original length to the new length, but this is a very easy way of approximating it. So what we're going to do is we're going to get this section here, maybe green wasn't, let me get a darker green. We're going to end up calculating this extra length here. So for that, we're going to end up using what's basically similar triangles. So we use our 75 degrees, and we know that actually it's vertical angles. If that angle is 75 degrees, then this angle is 75 degrees. So this section that we want here is going to be what is now the hypotenuse of a right triangle. .25 This hypotenuse is 0.25 millimeters. So the desired length is simply going to be 0.25 millimeters cosine of 75 degrees. So if we do that, we find that we get a delta L for AP is equal to 6.470. I'm using a lot of sig fig so I don't end up with a round off error, but we'll of course truncate as needed, and we'll keep that in millimeters. We can do the same thing with PB, and I'm going to look at just blowing this up a little bit here to show that a little bit better. Do a little strategic erasing here. I don't advocate drawing free body diagrams on schematics, but this is a really good way of showing the projections and how to apply this small angle approximation. So we're going to extend PB in its original line of action, and then we're going to assume we're going to pick some distance that we're going to designate as being our 0.25 millimeters. Drop a perpendicular, and so now this side, which is opposite of or adjacent to a 30-degree angle, this angle being the same as that angle, we can say delta L of PB equals, what is our hypotenuse? 0.25, 0.5. I think we have room here. 0.25 millimeters cosine 30 degrees. So that ends up being 8.6603 times 10 to the minus 4 millimeters. Okay, so we have changes in length for both bars. We have original lengths for both bars, 200 millimeters and 250 millimeters. So from that we can get strain, and I'll assume that everybody knows this means axial strain. We're not shearing the bars, we're just stretching them, so everything is axial or normal strain in the direction indicated by the axis of the bar. So I'll just go use the strain AP, not indicating, I'm not going to write axial. So strain AP is just going to be our change in length, our 6.4705 times 10 to the minus 2 millimeters. Divided by 200 millimeters. Oh, this calculation is incorrect. Apologies. Our change in length of PB, I'm reading the wrong line off of my calculation notes, should have been about 1/4 of a millimeter, which makes sense. 30 degrees is not a big angle, so we would assume that this cosine length would be not all that much less than our 0.25 hypotenuse. So correcting that error. Okay, so back to AP. Strain in the AP ends up being 3.2352 times 10 to the minus 4, and of course it's dimensionless since it's strain, and strain BP 0.21651 millimeters divided by the original length of BP is 250 millimeters. So definition of average axial strain, and that gives us a strain BP of 8.6603 times 10 to the minus 4. And we can see the two are similar order of magnitude, so that's kind of what we would expect. We would also expect maybe a little bit more strain in PB, simply because it's oriented closer to the direction of known strain. As an aside, we don't have any deflection, any displacement perpendicular to the vertical and then the horizontal, because we have these bearing surfaces. So we can imagine that there's a force from that bearing wall being applied to preclude any kind of stresses that would result in deformation in that direction. So everything is exclusively in the vertical. It's a bit of a 1D problem from that standpoint. Okay, now that we have strains, we can work through Hooke's law and get stresses. So we can get stress AP is going to be equal to strain AP divided by our modulus, So the strain is just simply that, and the modulus is our 200 times 10 to the 9th newtons per meter squared. And so this ends up being 64.7 megapascals, give or take. Rounds off. And strain BP will be, of course, stress BP will be strain BP divided by the tensile modulus, which is 200 gigapascals. And I'll just say where this came from. So strain BP, which we just calculated from the displacement using our small angle approximation, is the 8.6603 times 10 to the minus 4 divided by 200 gigapascals. So that ends up giving us 173.21 megapascals of stress in bar BP. And again, that does make sense that this would be more, again, because it's oriented more in the direction of deflection. Okay. Now, to look at force, we have to compare force to force. We can't compare stress to force. So the next step will be using what we have now and what we've determined about area, cross-sectional area. We're kind of given that. And take a look at how we convert from stress to, I'm going to change color here, to force. So we can get force AP is equal to stress AP times area, which is 1 times 10 to the minus 4 meters squared. And so that gives us a stress in the being exerted, gives us a force, a force being exerted by bar AP. Stress times area equals force is 6,470.5 newtons. Newtons being force units. And we do the same thing with BP. So force in the rod BP is stress in the rod BP, which we just calculated from strain and tensile modulus, times that same cross-sectional area. They both have the same cross-sectional area. So from that we get 17,320.6 newtons. So now all we have to do is apply a free body diagram. I'll stay in blue for our FBD. So we look in the vertical, and we can basically do an FBD of point P, and say we have a force pulling backwards, because we've put both of the bars in tensile stress. They've stretched. We know they're in tensile stress, which would lead to a force that would correspond to the stretch, which means if point P is pulling on the bar to stretch it, it's in tension. That means the bar pulls back on P. So we're going to have a force due to AP that is up in this direction, and we have our 75-degree angle here to the vertical, and our force magnitude is our 6470.5 newtons. And likewise we have force, tensile force exerted by our rod BP due to its stretch, 17,320.6 newtons. So if we take the y component of both of those, and note the point P is not accelerating upward or downward in the vertical, we can get force F is simply our cosine 75 degrees times 6470.5 newtons plus cosine 30 degrees times 17,320.6 newtons. Probably could have rounded that off and been okay. So if we walk through our math, which I'm doing live math, 75 cosine times 6470.5, then 30 cosine, 17,320.6 times, plus we end up with a force of around 16,674.75 newtons. So, well, it's 16.7 kilonewtons. So, to recap, to approach this problem contextually, first we looked at the displacement of point P, which presumably we could measure. We related that to the stretch, the lengthening along their axes of AB and BP. We made our geometry easier by using our small angle approximation. So we got a change in length. We knew the original length, so we were able to get strains, axial strains in both. We had the modulus of the bars, so we were able to get stress in both. We had the cross-sectional areas of both bars, so we're able to translate that stress into force. Then we did an FBD. We put point P into static equilibrium in the vertical direction. In reality, I should point out, the bearing surfaces are keeping point P in equilibrium in the horizontal. We don't have to worry about that. They're doing their job. So all we have to do is relate the vertical components of the forces that are being exerted by bars BP and AP due to their stretch and their tensile stress, sum those to zero, and the force that's being exerted is only in the vertical direction, so we just basically sum the forces in the vertical direction and set them equal to zero, found that our vertical force was about 16.7 kilonewtons. So that's an example of how we can work back and forth from a measured displacement and known characteristics of materials and cross sections and original part dimensions to getting forces. We could have worked this problem knowing basically any set of those values, such that just so long as we had the same number of equations as unknowns, we could have solved for any one of them. And which ones you'll encounter basically depend on whether you're doing maybe an analysis or capability assessment of a known structure, or you're designing something to fit a known set of loads and constraints. So that's it for this example.